In past videos, we have talked about detecting a sequence of bits within a long binary sequence. In this video, we're going to talk about generating that sequence. Periodic sequences generated in hardware are very important to computing. We use them for all sorts of things. For example, generating test sequences in order to use with our hardware. We use them to generate pseudo-random numbers. We also use them with slight modifications in order to generate CRCs that validate serial communications between two devices. In this video, what we're going to be talking about is how to generate those sequences in hardware and what sort of tweaks we can do to the system in order to make those sequences very robust. We're going to introduce those sequences by starting with the decimal integer sequences that we talked about in our discrete math series. And in fact, we're going to do a really simple one. If you recall, if we had, let's see, a sub k is equal to 2 times a sub k minus 1. And in order to figure out that sequence, we had to have some sort of an initial value. We call that a sub 0. I'm just going to start with 1. Now, I'm going to list an iteration, all the iterations or the steps for this sequence. So we're going to start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll get to 11, maybe 12. Do we have room in the board for 12? Yes. All right. Now, this first one, the 0th iteration, this is what we're going to refer to as the seed, the starting point for our sequence. Now, this term we're going to use a lot whenever it comes to hardware. It's something that we initialize the hardware with so it can begin generating its sequence. Let's talk about this particular sequence. So at the seed level, we've got a sub 0 is equal to 1, and then times 2 is 2, and then we have 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, and what is it, 4096, all right? Keeps growing, right? Now, what if we made a slight modification to this? In fact, the modification really is nothing more than let's just change the seed. Let's see what happens with that same exact sequence, except we're going to start with 3 as our seed. So this becomes what we have: 3, 6, 12, 24, 48, 96, and then we go to what, 192, and then 384, and then 768, 1536, let's see, 3072, 6,144, and then 12,288. All right. Different sequence. Same algorithm though. The only difference, the only thing we changed was the seed. Hey, let's try changing the seed again and see what happens. We'll make our seed equal to 0. What's going to happen now? Well, 0 times anything is 0, right? So we're going to start with 0, and it is just going to stay 0. Not really much of a sequence. Doesn't give us, there's no real purpose. It's just a constant. There's no reason for hardware. There's no reason for the algorithm at all. We just simply output a constant 0. When we're doing things in hardware, we have a limited or restricted number of digits we can use. And when we're talking about binary digits or bits, we're going to have a limited number of bits we can use. Well, whenever it comes to mathematics, we can limit our digits in a slightly different way by using the function, the modulo function, the remainder function. If you remember the modulo function, what it said was the modulo m is basically that number divided by m, whatever the remainder is. That's why we sometimes refer to it as the remainder function. So I'm going to do exactly the same thing. I'm going to go back to our key. So here's we still have this same algorithm. I'm going to do a sub 0, go back to 1, but now I'm going to do modulo, mod, sometimes referred to, we're going to do mod 15. Now, what's going to happen is 1 divided by 15 gives you a remainder of 1, 2 divided by 15 gives you a remainder of 2, 4 divided by 15 gives you a remainder of 4, 8 divided by 15 gives you a remainder of 8. 16 divided by 15 gives you a remainder of 1. And what you see is we looped back to our initial value. And what we've got is a cycle here. And in fact, if you complete this, starting at 1, so 1 times 2 is 2, mod 15 gives us a remainder of 2, and then 2 times 2 is mod 15 is 4, 2 times 4 is mod 15 is 8, and then it loops back to 1. And so we get this cycle, all right? What we've got here is something we're going to call a period. And the period, in this case, is equal to 4. We go through 4 elements before we cycle back to the beginning. Now, what if we used a different modulo? What if we used, once again, a sub 0 equals 1, but this time did mod 13? All right, so we've got 1 divided by 13 gives you a remainder of 1, 2 divided by 13 gives you a remainder of 2, 4 divided by 13 gives you a remainder of 4, 8 divided by 13 gives you a remainder of 8. 16, however, divided by 13 gives you a remainder of 3. All right, and then, so we didn't cycle because we have that different limit. So let's do 1, 2, 4, 8, 3, and then we have 6, and then we have 12. Now 12 times 2 is 24. Mod 13, however, is 11. And we keep going. Our sequence looks like this. All right. And in fact, we do not come around until after we go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have mod 13. We actually go through 12 different values, and none of those values are repeated because once we have a repetition in that sequence, we're going to create a period because we're going to start back over from where we left off. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All right. And so we actually, in this case, we have a period of 12. So period equal to 12. Let's do this one more time. Let's do same seed, except this time we're going to do mod 16. And what we get is 1, 2, 4, 8, 0. And then once it gets to 0, 2 times 0 is going to stay 0. And so we don't have a cyclic sequence here. And in fact, once you hit 0, really our period is what? 1? No, not really a period. Now, one more thing that I want to talk about in terms of this sequence. We're going to do a slightly different seed. We will go back to this mod 15. And this time we're going to start with a seed of 5. Now with a seed of 5, start out with 5, and then we do 2 times 5, that's 10, and then 2 times 10 is 20, but 20 mod 15 is 5. And so we're going back and forth here between 10 and 5 all the way down. And so what is our, and things are not lining up down there, but it's all on the board at least. What is our period in this case? Well, our period in this case is period equals 2. All right. And so you can see that by changing the mod, by changing the seed, we get different periods, we get different types of cycles. We're going to see that we get similar characteristics whenever we implement this in hardware. If you watched any of the videos in the computer organization series on our single cell memories, in other words, the memories that can contain just 1 bit, you probably saw our discussion about the D flip-flop. And the D flip-flop, well, it had 3 inputs in particular that we were worried about. One input was D, and that was where the data we wanted to store was set. So you put a 1 or a 0 here at this input. And then we had Q, which showed what was stored inside of the box. And then we had this thing called a clock. And the clock determined when we stored D into the box. And so let's just think of it as the button on a camera, right? So you can point your camera at whatever you want, but until you click the button to take the picture, nothing gets stored. So you look at the clock as taking a picture of what D is and storing it in Q. Well, if I put a bunch of these guys in series, I'm going to put 4 of these guys in series. And I am going to make it so that the clock is connected to the same inputs, or excuse me, the same signal. All right. Now, I'm going to cascade these so that the Q from one goes into the D of the next one. All right. Now, if I put a 1 or a 0 here, when I get a clock pulse, it's going to get stored in the box. If I put another value here and I get another clock pulse, then all the values that are in these D flip-flops are going to move one to the right. So every clock pulse, everything's going to move one position to the right. Now, this is called a shift register, and it is a very important component whenever it comes to hardware design for computing systems. What we're going to do, however, is create something called a ring counter. Now, a ring counter simply takes the output, wraps it around so that it becomes the input for the system. And so if you were to look at, for example, let's just call this A, B, C, and D. And so I'm going to have a little table here, A, B, C, D. Let's just say that these are the values that I have at the first iteration. Get a clock pulse. The 0 that's in the D comes into the A, and then everything else gets shifted over by 1. All right. And I get a clock pulse, and the 0 that's in D comes into A, and everything gets shifted over by 1 position. Get a clock pulse, the 0 that's in D goes into A, everything gets shifted over. Get another clock pulse, this 1 that's in D gets shifted over. And it's just this staggering, this diagonal matrix of all the values that are in these latches. What our goal is today is to create a sequence generator using this ring counter. Now, the way we're going to do it is, well, turns out there's 2 ways. The first way that we're going to do it, and remember, whenever we looked at generating those sequences in integers using those equations, we had an algorithm. The algorithm we used was that a sub k is equal to 2 times a sub k minus 1. Well, we need an algorithm here. And so we're going to call this algorithm just a linear function. All right. And this linear function is going to take any number of the inputs from our ring counter. So it may or may not include the value A, may or may not include the value B, C, and D, and so forth. Actually, there is one that is always going to be included, and that's D. Because if D were not included, then we wouldn't even need to have this last flip-flop, because then C would be enough to drive the linear function, and all we would require are those 3 flip-flops. So the last one in the line, the one that outputs to be brought right back around the front, that guy is always going to be contained. Now, this particular thing, this particular circuit, is referred to as a linear feedback shift register. And actually, this is just one type of linear feedback shift register. This is specifically an external. There is an internal linear feedback shift register, otherwise known as an LFSR, where instead of the function being on the outside, in other words, taking all the values, creating a single function, and routing it back around, the function is actually between the latches. So what you've got is the D, Q, and clock, and then you've got a linear function here, and then it goes into the next D flip-flop, D clock and Q, and then you've got another linear function, different linear function in here, and it goes to the next D latch and so forth. Well, the one we're going to talk about is the external. This is the internal. We may talk about that in a later video. Now, there's a couple of things that we need to know about. First of all, the linear function. It is made up from exclusive OR operations, all right? When it comes to just the 2 input exclusive OR, what you've got is, and I'm going to draw the expression here, so you have A or B in our truth table, A exclusive OR B. If we have the same inputs, if both inputs are the same, we output a 0. If they're different, we output a 1. So this linear function made up of exclusive OR operations, one of the things that's important to see is that if I have two zeros, we output a 0, which means that if I have all zeros here, then the output of the linear function is going to be a 0. Guess what? We're stuck in that situation like I showed you before, where we had the seed value of a 0, never gets out of a 0. It always stays a 0. That's not a very interesting sequence. In fact, it's not a sequence at all. It's just a constant. We just connect it to a 0. We're fine. The deal is that the values in these latches, if it ever goes to 0, you never get out of 0 because the linear function always is going to be outputting a 0 and it'll just stay there. So we avoid all zeros in these latches. Now remember, the initial value that's being put into these latches, that's referred to as the seed. So the seed is going to be a non-zero value that we put into there. Now these points of connection, for example, A being connected to the linear function or B being connected to the linear function, these guys are referred to as taps, all right? We're tapping off of this shift register at different points. Now remember, as I said before, this last one in the shift register, this last bit of the shift register has to be tapped. If it's not tapped, then that whole shift register is not necessary. What we've done is delayed by one clock pulse the value of C coming out into the world. It has to be included. So D has to be included, or this rightmost one has to be included. But these guys are optional. So you may have one or more of these guys included in the linear function. Let's start out with a simple example. In fact, it's going to be very simple. It's just going to be a 2-bit shift register. So there's just going to be 2 bits here. So Q goes into D, and then we've got this output Q coming here. We're going to call this A and B. And remember that we've got a common clock that is going to be driving both of these D flip-flops. And remember, the clock input looks like this weird little triangle that's attached to the side of these D flip-flops. All right, and so we've got our linear algorithm up here, and our linear algorithm is once again going to be made up of these exclusive OR gates. In this case, we have to have the last one because remember that if we didn't have the output of the last flip-flop as part of the linear function, it doesn't even need to be included in the circuit. And there's only one other signal to be included. Now, there's a couple of ways that we could draw this exclusive OR. The symbol for an exclusive OR is typically the plus sign with a circle around it, but I'm going to actually use the logic gate that we use to represent an exclusive OR gate in circuitry. And that is kind of these 2 little curved lines going into a pointed gate. This is like an OR gate with a second line here. And that's going to come back around. There's our exclusive OR. Now, remember, if the bits are different, this is going to output a 1. If the bits are the same, it's going to output a 0. Now, remember, we need a seed value, something to start with. So I'm going to have just these 2 inputs, right? And I'm going to talk about whatever cycle or iteration we are on. So at the beginning, our seed value, I'm just going to put 1, 1 as our seed value. Now, A exclusive ORed with B, that's supposed to be an exclusive OR, right? Eventually it'll squint, it'll make sense. All right, so they're the same, so the exclusive OR is a 0, which means that on the next cycle, when we get a clock cycle, this 0 is going to go into A, the A is going to go into B. Now they're different, the exclusive OR is a 1. Next clock cycle, we get that 1 goes into A, the 0 that's in A gets passed to B, we have different. Now there's a 1 on the output. Now this one on the 3rd clock cycle is going to go into A, and then the one that's in A is going to go into B, and we get our original seed, all right? And so this is going to cycle. So what is our period? Our period is 3. All right, and we've gone through every single value for A and B, 0, 1, 1, 0, 1, 1, except 0, 0. And remember, we can't have 0, 0, because once we get a 0, 0 there, then the output of our exclusive OR gate is going to be 0, and we'll always be in 0, never get out of it. And so something important to notice here, with this particular circuit is that we have 2 bits, so n is equal to 2, And 2 to the n minus 1, well, that's equal to 2 to the 2 minus 1, which is equal to 3. That is going to represent our period, the maximum number of cycles we will go through. This 3 right here is the maximum number of cycles we will go through before we loop back around to an original value. In our next example, we're going to go to 3D flip-flops. So I've got 1, 2, 3. They're all in series for our shift register. So we've got, and we'll call this A, B, and C. So A drives B, B drives C. Each one of them, all 3 of them, excuse me, are driven by a common clock. So there's our clock, right? We're going to tap off of A and C, all right? And that's going to come back around into the input of A. So there's our feedback circuit. Once again, this is the external linear feedback shift register. So what does it look like? Well, we're going to do the same sort of thing again. We're going to have our cycle, right? And then this time we have A, B, and C. And input to A, so we've got the input to A, that's going to be the exclusive OR of A with C. And we're going to have our seed value. We're going to put 101 in here. Now, A and C are equal, so our input to A is going to be 0. So the 0 gets passed to A goes to B, B goes to C. All right, so this is cycle 1. Now, A and C are the same, so now we've got a 0 in AN. So that 0 goes into, for the second cycle, that 0, this 0 gets passed to A, the 0 that's in A goes to B, the 1 that's in B goes to C. Now they're different, so the exclusive OR is a 1. So in cycle 3, A has a 1, B has a 0, C has a 0. So you see this shifting, these diagonals, right? A is different than C, so the exclusive OR is a 1. So in cycle 4, we've got A is a 1, B is a 1, C is a 0. Still different. So in cycle 5, we've got A is a 1, B is a 1, C is a 1. Now we have a 0. Notice we haven't yet made it so that the pattern that is in A, B, and C has looped around back to our seed or any of the other previous values, but let's keep going. So cycle 6, we have the exclusive OR of 1 and 1. That goes into A, that's a 0. And then B gets A's 1, C gets B's 1. Now we've got A and C are different. That gives us a 1 for the exclusive OR. So in cycle 7, we have 1, 0, 1, which brings us back to our original seed value. So what is our period? Well, our period, we had to go 1, 2, 3, 4, 5, 6, 7 cycles. So our period equals 7. All right. Now, once again, it just so happens, this doesn't always happen. It's based on a proper selection of the taps. But in this case, the taps that we selected gave us a period of 7. We have n is equal to 3. So 2 to the 3 minus 1, 2 to the 3 minus 1 is equal to 7. So that means that this particular set of taps gave us the maximum period we could get. This 2 to the n minus 1, that is the maximum period. And remember, we have this minus 1 because 0 cannot be included in our sequence, or else it will give us it will be stuck in 0. One of the things I want you to notice is that this value that's in C, it's almost as if we've got these coin tosses. So you could coin toss, get a heads, and then a tails, and then a heads, and then 2 tails, and then 3 heads. And it looks like it's almost a random sequence of coin tosses. This right here can actually be used as a pseudo-random generator. So we're going to see how to use this in a later video. But in the next video, we're going to start with a periodic sequence and determine, first of all, the required number of bits that we need, and determine what the external linear function is in order to generate that sequence.